lecture. Okay. All right. And today is going to be the last material on thermodynamics problem. All right. So we're going to stop everything about thermodynamics after today's lecture. So we complete the thermodynamics module. All right. And today I am going to use this example. I'm going to go through this problem with you guys one more time. I will take this chance to review what we have been doing since the beginning of thermodynamics up until at this point. And I will show you how to apply the first law of thermodynamics. Okay, one more time. And after that, we will give you to see a little bit of second law of thermodynamics, which it's going to be talking about the reversibility of a process that the first law cannot do. Okay, because the first law only take care of the conservation of energy. It doesn't really give you the direction of things that is supposed to change. All right. So let's dive into it, shall we? All right. It's going to be a lot of fun today. A lot of confusion today because we are talking about the second law. Okay. All right. So I think up to this point, you guys have already probably familiar enough with the material, and something that I think I would say is the biggest wow from last time was just like talking about the best engine in the universe. All right. And that was the name. It's the Carnot engine. Okay. And we try to understand those by looking at the reversibility of a process. Okay. So that's what we did last time. So take a look at the first law of thermodynamics. So now we understand that we have three terms. All right. Three terms that you need to know how to deal with those. So first is going to be the delta U, the change of the internal energy. And now you know there are two ways that you can exchange or transfer energy in or out. It's either by heat or it's either by work done. Okay. So this is it. Pretty much that is the first law. Okay. However, when we were looking in this scenario over here, the one that you have gas freely expand inside an insulated container that cannot expand or contract. So that means in this case, you have no work done because the wall are insulated on all sides. You don't have any heat exchange. So that means by first law of thermodynamics, you say that your internal energy will not change. When the internal energy does not change, your temperature will not change either. Okay, so cool. First law is pretty much like done there. However, we were talking about last time that if the gas expands, so gas will fill up the whole space inside this container, and gas laws still apply. So you have PV equal to nRT. So that means you have PIVI over TI equal to PFVF over TF. All right. So because the gas expands twice as big as the original, you can say the pressure will drop in half. That's fine, no problem. All right. But the thing that we were talking was like, hey, this process is one way. There's no going back. Yeah.
Okay.
So with that, then that means, all right, first law cannot take care of the direction of the change. Okay. But it's pretty good. All right. It's pretty good in the sense that by just grabbing this first law of thermodynamics along with the gas equation, you will know how to build the best engine in the universe already by combining isothermal process and the adiabatic process. And that will lead you to this heat engine with the highest efficiency possible in this universe. Okay. And getting to this, we have a chance to talk about irreversibility of a process. And that has a little bit of the connection to the second law that we're going to discuss further today. All right. But stopping at the first law, we're going to do one more exercise. All right. So this is what we need pretty much. The first law of thermodynamics and the gas equation. That's what we want. Okay. Let's dive into it, shall we? All right, guys. So if this is the question that show up in the exam, and it's pretty good, this is a very good level of the difficulty that you're going to face in the exam. I think it's not going to be way harder than this one. This is it. All right. So don't worry about the difficulty level of the exam questions. I'm not trying to, shoot you guys with like, super duper hard question or anything. It's going to be just a plain, straightforward problems that you should be able to solve using the understanding that we learned in class. All right. So give it a shot, shall we? Yeah. Okay, guys, go ahead. Okay, just kidding. All right, we go through this one together. Okay, what is the thermal efficiency of an engine that operates by taking n moles of a monatomic ideal gas through the circle shown in the figure? It's pretty good. It's simple enough. You can see, oh, Ajahn, I can see it's constant volume process from 1 to 2. Okay, and then followed by constant pressure process from 2 to 3. And then constant volume again down 3 to 4. And then you end everything with back to 1, complete the cycle with the constant pressure process. That's doable. All right. So just to make this one as a review of what we have been doing all along. So let me go through, assuming that we're going to start from the beginning. Let's look at the segment 1 to 2, shall we? All right. And let's try it. Okay. First thing first, let me mark on the side here, delta U equal to Q minus W. That's the first law of thermodynamics. Okay, so from 1 to 2, guys, what do you know? Well, hold on, let me attack the easiest one. W is equal to 0. No work done. Volume does not change. Yeah? Okay. So when the volume does not change, all right, then I don't need to do anything. W is gone. So from the first law of thermodynamics, delta U equal to Q. But you guys know already, okay, let me mark on this side here, for the monatomic ideal gas is 3/2 nRT. Cool. So with that, that means this is going to be delta, let me write it like this, 3/2 nRT. Think of it that way, all right? Or we already did this, it's a 3/2 nR delta T. All right, and stick with the delta. Every time you look at the delta, it means you're doing the final minus initial all the time. So that means it's supposed to be 3/2 nR T final. It's point number 2 right here. So it's going to be T2 minus initial temperature, T1. Cool. Stick with the order of the delta. The sign will be automatic at the end. All right, that's what we learned. Okay, now you don't have the information about the temperature. You only know the pressure, you only know volume because you are given the PV diagram and everything. So no problem. You apply the equation of state, PV equal to nR. Oh, I think maybe I need some space there. Okay, so I combine this with PV equal to nRT. So that means I can write nRT to be just P times V. So it's going to be 3/2 nRT. Oh, sorry, nRT1. nRT2 is going to be P2V2. You guys with me? Okay. Minus nRT1 is going to be P1V1. And now you just read the scale of this value here at point number 2. Oh, Ajahn, I know the pressure and volume. Just substituting in 3/2. Pressure at 2 is 2 P naught times the volume at 2 is V naught minus P1V1. It's right here. P naught, V naught. Very nice. And that is it, guys. Done. So it's a 3/2 P naught, V naught. Good to go. Okay. Cool. And this is the Q. This is the heat as well. So what I'm saying over here is, oh, Ajahn, we already knew how to calculate the total and the internal energy change, and that will be equal to the heat flow. So what you can say is this is going to be the heat during the process 1 to 2 as well. And you're done. It's positive. So that means heat flow into the system. I can draw, I can draw an arrow like this just to say, hey, guys, there's a heat flow in 1, 2. Isn't that cool? Okay. Done for the 1, 2 section. Right. And for those of you that still sort of like, all right, remember vaguely, Bajan, because we really want to calculate heat, we have like some sort of like a shortcut that we can just dive into the Q right away without going through the work and the internal energy change. Yes, you can go through heat during a constant volume process by writing it as the NC sub V delta T. Remember that one? Yeah. Okay. Yeah. So because of the monatomic ideal gas has a C sub V of 3/2 R. So this one go through 3/2 N R delta T. And as you can see, it's look exactly like here. Same thing. Because we derived this last expression from first law of thermodynamics anyway. Yeah. So there's no surprise. Okay. So that means you can use this last line over here to pretty much like, jump to the final conclusion right away about the heat. That is going to be 3/2 in R delta T. And then you just follow the calculation and then you eventually arrive at this value as well. You are done.
Okay.
This is a good review, I hope. All right, because this is like we do everything from scratch, from the first law of thermodynamics. Okay, try one more, shall we? Let's go from 2 to 3. All right, so what do you know? Bajan, what I know is, once again, the easiest one to do in the PV diagram is calculating the work by the system. Is just the area under the curve. So that can be done. So going from 2 to 3, the work done is just going to be the area beneath that line. So let me highlight it in yellow here. There you go. All right. There you go. All right. There you go. Okay. All right. That's the area there. That is your work during this process. So W is just going to be, okay, if we start from scratch, it's going to look like integral P dV. Yeah, remember that one? Yeah.
Okay.
Just a little bit of calculus. Yeah. And then because pressure is constant, you pull P out. You just have the integral of the dV going from 0.2 to 0.3. But then the integral of dV is just V. So that means it's just P delta V, or it's a P V at 3 minus V at 2. See that? All right. And by writing like this, it's just the pressure at that point multiplied by the change in the volume is just the width times the height. P times delta V. Yeah, delta V is here. That's your delta V right there. Cool. All right. So that means I can calculate work done by saying that the pressure over here is going to be 2P naught. Volume at 3, it's 2V naught. Volume at 2 is V naught. So the difference is positive V naught. So let me write it down. 2V naught minus V naught here. So it's going to be 2P naught V naught. Am I right? Yeah. Okay. And that's it. That's for the work area under the curve. Good. So far, so good. All right. Next. What about the other two that we have left? Which one you want to attack first? Of course, Rajan, usually we're going to do with the U because we know the formula for U. So let's find out what is the change in the internal energy from 2 to 3. Okay. Once again, 3/2 N R delta T. So take final minus initial all the time. So it's going to be temperature at 3 minus temperature at 2. We don't know temperature, that is fine. nRT equal to PV anyway. So it's going to be 3/2 P3V3 minus P2V2. Cool. Nice. What else? Substituting the value. Pressure at 3, 2P naught. Volume at T at 3, 2V naught. So it's going to be 3/2 2P naught 2V naught. That's for point number 3. You guys still with me?
Okay.
I'm not alone, yeah? All right, minus P2V2. Look at point number 2. It's a 2P naught, 1V naught. Okay, 2P naught, V naught. So there you go. Alrighty. So what you have here is delta U is what? It's like 4 minus 2 is 2. 2 cancel with 2. So it's a 3P naught, V naught. That is your delta U.
Okay.
All right, guys. And the Q is going to be straightforward because Q is just delta U plus W. Yeah, from first law of thermodynamics again. So delta U is already 3P naught V naught. We just got that one. W is 2P naught V naught. So total is 5P naught V naught. And you are done. That's it.
Okay.
And you can name this one Q from 2 to 3. And once again, it's positive, guys. So it's positive means heat entering the system. So there is a heat flowing into the system. Let me call it Q23. Isn't that fun? All right. Plus, once again, I can sort of like, jump ahead. I don't have to go through this first law of thermodynamics, going through crazy stuff, because if we really want just the heat, I can do it through NC sub P delta T, because this one is just constant pressure process. And we know that the molar specific heat in the constant pressure process, C sub P, is 5 half R. So it's going to be 5 half NR delta T. All right. And if you sort of like do this one, okay, let me complete this one for you guys. 5 half NRT final at 3 minus initial at 2. Now you start to see what is supposed to be now. 5 half NRT is just P times V. Cool. Read the value, plug it in, 5 half. So at point number 3 is 2P naught, 2V naught. So it's going to be 4P naught, V naught. Minus at point number 2, it's 2P naught, V naught. And as you can see, you get exactly this one. Check. Good.
Okay.
You guys still with me, yeah? You guys so quiet today. All right, but anyway, you still not. I mean, you guys not mad at me, yeah? You still okay, right? You guys forgive me for the last Saturday already, right? All right, so that's the heat calculation. All right, so I can put the subscript here. It's a 2, 3, and that one can be 1, 2, exactly the same. There you go, same thing. Nice. Okay, so I hope by showing you these two segments over here, that give you a good review of what we have been doing, applying the first law of thermodynamics along with the gas equation to analyze thermodynamics processes. Yeah. But anyway, we're still not done yet. This problem asking you to figure out the efficiency of this engine. All right. So at the end, you're supposed to keep doing, because you still have segment 3, 4, and 4, 1, right? However, I'm going to show you one more thing here. You can actually keep going and calculate the other two segments, but by understanding of the whole, thermodynamics processes and everything already, you should be able to guess already what will happen from point 3 to 4. Supposed to be sort of like reverse in directions in comparison to going from 1 to 2. You guys with me here? Okay, because 1 to 2, you're going up, right? You increase the pressure, you draw in the heat. 3 to 4 is kind of like reverse. You're going down by keep the volume fixed. So that means you can probably know right away the heat 3, 4 is supposed to be going out. That means if you do the calculation, you're supposed to get a negative heat. Cool. Same argument for go with the 4 to 1 process. It reverse in direction in comparison to 2 to 3 up here. So when you look up there, going from 2 to 3, you expand with a constant pressure, you draw in the heat. So when you go from 4 back to 1, you compress the gas by keeping the pressure constant. So you can probably guess that the heat probably flow out. It's going to flow out from the system. Yeah. And this is good, Bhutan. This is very, very familiar picture over here, because we keep saying about heat engine that you have a diagram. You're going to have Q hot coming in, and you're going to have a Q cold going out. And whatever left over, that is going to be the work done. Yeah. So this is what we like to compare between the two. So let me sort of like give it like a box here. There's a diagram. So what do you see over here is, do we need to sorry, do we need to really calculate Q34 and Q41 or not? The answer is you can, but there is an alternative. The other thing that you can do is, why don't we calculate the W instead? Because we already learned as well, the work done by the system in the cyclic process will be equal to the area enclosed by that process. Remember that one?
Okay.
So come back here again. So this one is a cyclic process. Okay. So 1 to 2, no work. 2 to 3, that's the yellow area over there. 3 to 4, no work. And then 4 back to 1, you're going to generate work done equal to the area under the curve, right? 4 to 1. Here we go. Here we go. Here we go. Here we go. Yeah. But this area from 4 to 1 is going to give you a negative work done because it's the compression. It's a negative work. So think in terms of the area. It's just like you try to erase the yellow area out. Get rid of that. So that means by calculating the work done from 4 to 1, you're going to cancel the work done that 2 to 3 has been, already did earlier. So that means you're just going to cancel this portion of your work done mathematically, numerically. All right, there you go. So this one will disappear from the amount of total work done in this process there. Bam. See, what you have left is just going to be the area enclosed by this cycle. And this is so easy to calculate because you want the work done here. This is going to be W. And you know in your head it's going to be the positive value because, I mean, it's a clockwise rotation over here. So the yellow area is going to be positive work done. The black area that we already erased, that is a negative work done. So whatever you have left is still positive anyway. So the W here is going to be just this area, the width times the height. Cool. All right. So that means you just have the width is V naught. The height is P naught. And that's it, guys. I should put it in order over here. Sorry. It's P naught, V naught there. That's it. So that is a W. So you don't need to calculate Q34 and Q41. You don't need to because you already got the W. And once you get the W, you can get to the efficiency easily because efficiency is just W over Q hot. Okay? So the only last thing that we need is, guys, what is Q hot? Remember the previous exercise there? Whatever the heat that you have to provide to the system to perform whatever the things that the engine is about to do is just the heat that flow into your system. So that means your Q hot is going to be these two terms right here, Q12 and Q23. That's your Q hot. Okay, and the work done, you just got that one. You already calculate here. It's just P naught V naught. And that's it, guys. The efficiency of this one is, now I ran out of space a little bit, but I can squeeze in here. So the efficiency, all right, so let me erase this. All right, oh, give me some space here. There you go. All right, so efficiency is, there you go. Efficiency is W over Q12. Okay, I just take the magnitude. Q23. And that's it, guys. You are done. Cool. All right. W is known. Q12 is known. Q23 is known. You can calculate the efficiency of this cycle. Any question? Sounds like a good example over here. I think you guys too quiet today. It's just like you guys still mad at me, I guess. Yeah. All right, guys. So that is it for this one. And you will be able to find more exercises in the homework that sort of like, give you more work or more example for you to practice how to calculate each term in the first law of thermodynamics and eventually calculate the efficiency and compare it to maybe Carnot engine, on and on. Yeah. Cool. Whew. It's always like a long problem when you have to analyze the whole cyclic process and everything. Yeah, that's normal. So far, so good, guys. Still with me? Yeah. Okay. So any questions up to this point? Okay. Looks good. All right. So if not, Then we're going to move further. Okay. Once we understand this whole like basic, plus application of the first law of thermodynamics, now it's time for the second law of thermodynamics. Whew. Yeah, don't need that one. Here we go. It turns out the way that we will be able to quantify, because we want to quantify somehow, that if a process is reversible or not. So let's go back to our beloved example over here. All right, you guys know, if you just want to indicate the direction of the change, the first law doesn't give you anything. No, nothing. Right? That you need something else that eventually allow you to pinpoint, or at least to determine, like, okay, this is going to be the way it's supposed to go. This is not the way that system is supposed to go, on and on. So we want that quantity. And it turns out the quantity that we will be talking about is named entropy. All right, welcome to the show here, the entropy. Okay, so historically, entropy was named to go in the same sense of energy. So, and the hope initially was, I think, by scientists, or at the time, I don't think there were like physicists just yet. But anyway, those science, it's physicists already. So it's the idea that entropy is supposed to be as important as energy at first, right? But it turns out, if you have already observed, you haven't learned about entropy in maybe like a middle school or anything. You talk about energy all the time. Plus, in our everyday life and everything, we always talk about energy, right? No matter if it's about the food that we eat, about the electricity that we use, about whatever, like a solar cell, or fuel, gas, or car engine and everything. So we always keep talking about the energy. The reason for that, I think, is because the concept of entropy is not as important as energy. So, well, you probably don't need it because it's so baked into your system, or baked into our universe. Seriously. All right. So let me give you a test of what this is about. So it turns out, if you look at most of the textbook, they will start something like this. Entropy is a measure. Of course, we need some measure to indicate something about the system, but it's a measure of this, guys, disorder. Whoa, this is the killer here. How can we quantify disorder in your system? That is the main goal of today's explanation. Okay, and sometimes disorderness, or disorder over here, come along with the randomness of the system. Whoa. All right. So something is kind of sort of like go randomly. The greater the randomness, the higher degree of disorder, and that lead to something related to entropy. That's the key. But how can we quantify, or how can we define entropy that's eventually linked to the disorder of a system? So come back here, guys. Let's imagine that we're looking at isothermal process one more time. We love isothermal process because it's a process that does not change in temperature. Temperature does not change. So that means T is constant. Very good. And the good thing is no change in internal energy along with that. So that means from the first law of thermodynamics, the heat flow will be equal to the amount of work done in the system. So we can talk about the heat exchange in relationship with the work done. So if you have a tiny amount of heat flow in or out from your system, so let me put the differential symbol there just to say, hey, that's like infinitesimally small heat. Yeah. Super small, super small. And of course, during that exchange of that tiny bit of heat, you do a little bit of work. So let me put the differential symbol in front of the W. That's a tiny amount of work done. So we already knew by definition, the work is just the pressure times the change in the volume. So it's a PDV. And because we are dealing with ideal gas, we can re-express this P as a nRT over V. Cool. All right. So P is nRT over V. So that's nRT dV over V. Heat linked to this term. Now, what we are looking at is this term right here. So let me bring you guys here on the other side. What does this imply? I wrote here, it's implied disorder already. But why the change in the volume relative to the initial value give you something of the more disorderness of your system? Imagine this. I don't know if this is a good analogy or not, but this is something that I hope it will help a bit. Imagine that you are like maybe parents, okay, taking your kids to a playground, right? Kids running around, go crazy, right? Play this, play that, on and on. But then suddenly, let's say that your area that your kids can play is double in size. So it means kids can run around even further away from you. I mean, you kids going crazy in more places. There are more stuff that they can play. So for you as a parent, that's a disorder because like, oh my God, it was just harder for you to keep track of your kids on and on, right? So that's the idea. When you have more space for your kids to run around, that is greater disorder. So now bring back that comparison to something closer. Think about gas in a room. Okay, so gas can sort of like go crazy, travel. Okay, and they just bounce each other on and on. But then let's say suddenly this volume of this room is doubled. So gas can go further away. I mean, can run further. Can you have more space for gas to fill up? And then things are going crazy even further. So for you as an observer, you look at those gas molecules and seems like, oh my God, we have larger volume. So gas can have larger way that they can sort of like travel. There are more positions for you to keep track of. You have more places that gas can have different velocity, on and on. So all in all, what I'm going to say is larger volume means the system can have a greater configuration. Does that make sense to you? Yeah.
Okay.
When you say configuration means the way that you can arrange your system is greater. Another analogy, if that will help or confuse you more. All right, sorry. It's just like, think of it like a bookshelf. Okay. So when you have a bookshelf, then you can sort or you can store, you can keep your books and everything. So in place, nice and tidy. But think about it, if your bookshelf is double in size, so you have more choices or you have more ways that you can arrange your books. Does that make sense? Because now, okay, you have the upper shelf, you have a middle shelf, you have a bottom shelf. You can switch and then move things around on and on. So that's what I'm saying is you have more configuration that's available to you. Okay. And when you have more configuration, that's why it's linked a little bit to the disorder in the sense that because you have more, some sort of like more ways that you can arrange things. So there are more ways that things can go disorder. That's what it is. Okay. So in conclusion, that's why this term right here, greater volume or increase in volume, give you the size of the disorder of the system that is going to change. Okay, now look back at what you have left. So I can move nRT to the left-hand side. So the nR is going to be fixed. Nothing is going to change. So that means the only thing left for you is this dude right here. The heat flow divided by the temperature of the system at that point. And this is it, guys. That define the change in the entropy of the system.
Okay.
Okay, so you might still be, I still don't buy it. Okay, why? So we need some example, of course. But the idea is at least this dq over t directly related to this dv over v. And because we're going to define this one as the change, a little bit of change in the entropy, that's what we're going to try to help you to calculate this term and see, hey, is this a useful terms to define or not? All right, but at least this is the definition of the entropy. The good thing about entropy is this. Bajan, wait a second. I don't like this because we already discussed that heat is path dependent. You can have like, what kind of heat or whatever. I mean, you can heat things as many ways as you like. It depends on what you want to do. So if you define something like this, isn't that bad? Because now your S will go crazy. It's going to be path dependent and it's going to be something that's so hard to work on. No, we are going to do something that make entropy as good as energy, which means it's supposed to be path independent. Otherwise, then entropy won't be able to act as a state variable, right? We want something to be a state variable because when I look at it, I can calculate entropy. Okay? And then when I look away and the system change, I open my eyes again, I should be able to calculate entropy one more time without knowing what has been going on with the system. Just like energy, okay? When it's here, let's say this is my reference point, everyone knows gravitational potential is 0. Okay, when I put it up here, it's mgh. When I put it back down again, it's 0 again. So I can turn away, look back again, it's 0. It doesn't matter. It might have already traveled, through space and over, come back here. Everyone can tell energy is 0 here. It's path independent. We want that for the entropy. Yeah, otherwise, then it's going to be pretty much useless here. So how can we define entropy that link to the heat, but then it's still path independent? So there must be some restriction on the heat that you're supposed to be able to use in this definition. And that's what it is. It turns out it's not any heat that you can put into this formula. It has to be the heat that you calculate from a reversible process, guys. Yes. Does that make sense to you? So if not, here we go. Remember this one? We discussed at length about the reversibility using this example over here. So we were so concerned about the heat that get lost forever. I mean, this is like gone, Adan. This heat is not accessible to us anymore. When you have the temperature change and there is like a phase transition, things warms up, things cool down, on and on. This is the heat that is got to be lost forever. This is not good. We don't like that one. What we love is the one that is still available to us, and that is the one that happens in the reversible process. So this is the heat that you can account it for, and hopefully it can be sort of like used for something useful later. All right, that's what the discussion about the reversibility and irreversibility, right? So that's why this is the one we want. We're only going to calculate heat from a reversible process, because reversible process is going to be the process that you can draw on a PV diagram.
Okay.
Right? Because we already said, John, well, how can we figure out heat from reversible process? Well, it's easy. We use PV diagram all the time, right? And we said every time you have a line or a curve or a process in PV diagram from initial point to final point, you can put an arrow into it and say, okay, this one going from initial point to final point, right? But then your friend can just come in, well, hey, Ajahn, let's flip the whole thing. Let me go backward. No one has a problem with this, right? You can reverse the whole thing because we assumed that everything that can be drawn in a PV diagram is something that happens slowly. You can measure pressure, you can measure temperature and everything like in equilibrium points. Everything is already nice and smooth, thing goes slowly. Every point in the system is uniform. You can measure temperature at any point in on and on. So that was the requirement that we will be able to draw a curve in PV diagram. So does that make sense? So that means in conclusion, don't worry about these heats. All you need to do is you just get the heat calculated using some kind of like PV diagram or something that you have already learned from thermodynamics previously. That's good. Cool. All right. So as long as, think of it this way, as long as you can describe that change using a curve in a PV diagram, and then you use that curve to calculate this heat, that is good. That is your reversible heat already. Cool. Okay. All right. So I'll show you with an example. It will be a lot clearer at this point. But anyway, up to this point, that is our definition of entropy change, is the heat transfer divided by temperature at that point. So if you want the total change of your entropy, all you need to do is just integrate them up from initial point to final point, and then you will end up with the total change of the entropy is just the integral of dq over t. And that is guaranteed to be path independent. And the good thing about the independency of path is if you talking about the cyclic process, okay, and of course, when you say reversible, it means you can represent it using a PV diagram somehow that you have already seen before, whatever process that you have run in cycle, entropy change will definitely be zero. Isn't that cool? Well, just like energy. MGH, you go across the universe, come back here, no energy change. Cool. Entropy will do the same thing. So if you have a cyclic process, entropy change will be zero. Okay, but then we have sort of like a crazier business to do. Well, Ajahn, that sounds easy, but how we are going to calculate those? Okay, so what happened to the irreversible process? So come back to our beloved situation again. That's insulated container with the gas occupy the bottom half of the container initially, and then the membrane breaks, gas fill up the whole space. Be familiar with the situation. No heat, no work, no nothing. Temperature stays fixed, the same, no change. Okay, volume go twice as big, pressure drop down in half. Now it's our time to calculate the entropy change of this process or this scenario over here. So before we do anything, how are we going to do that? That's the question. So before the break, I'm just going to give you a question here. So you can think about this during the break, and then you can answer it after the break. So I'm just going to start with the PV diagram, because eventually we're going to need PV diagram to calculate heat anyway. So let's say that my initial pressure is P naught somehow. So everyone knows after the expansion, the pressure will drop in half, right? In compensation, that's the volume increase twice as big. So that means initial point, it's going to be at the initial volume V, and the pressure is going to be P naught right there. So let me point it out to be here. This is my initial point right there. Let me call it point 1 or point I, doesn't matter. Same thing, that's initial point. But then after the expansion, your volume go twice as big. So now that's U2V, but then your pressure drop down in half. So it's going to be P naught over 2. That is your final point goes here. That's point number 2 or point F. The question I want you to think during the break is here. Oh, no, not that big. So what is going to be the curve that explaining this this gas expansion process? That is my question. Okay, come again. Going from point 1 or point I, initial point, to point 2, the final point, for this process, what should be the curve that explaining this scenario that we are analyzing? Okay, think about that. And I will give you the answer after the break. Sounds cool? All right, guys. So let's take a break right here.
Okay.
All right. See you in 10 minutes. Sounds good? Yeah, 11. Okay. So, all right. We'll see you in a bit. Yeah. All right, guys. So the answer is this. It cannot be done. Oh, no. I don't know, is like, what kind of answer is this, right? So the answer is cannot do it. Why? Because this is a process that, well, first of all, is irreversible, one thing. But the other thing is it's super fast in the sense that things are sort of like going crazy after membrane breaks. So gas will start to expand into the vacuum. So imagine this, if I am someone standing at the upper right corner of this container, at the moment that the membrane breaks, I don't feel anything. Does that make sense? It's just like, I don't feel a thing because gas haven't traveled to me yet. So I still don't have any pressure. I still don't have, well, to say, if it's really, really vacuum, I still don't even have any temperature here. Plus, during that dynamics thing, right? During that process that gas is filling in the space and other stuff, there is no single value that can represent the pressure of the whole gas. There's no single value that will represent the whole temperature. Does that make sense? So that means during the full thing, during the time that gas about to, so like during in the process of expanding, it's blur. How can I say? It's just like, well, I don't know what's going on here. I have no idea, but I know at the end it's arrived at point number 2. So that means, yeah, this I can call like the gas expansion process over here cannot be represented using a PV diagram, guys. This is a very good exercise, or as a good example, just to showcase that there are some real situation that cannot be represented easily with the PV diagram. Okay, cool. I don't know, does that help a little bit? Okay, but of course, if you wait maybe just a second longer or 2 seconds longer, you will take a look at the system and everything just look like the second half of the diagram over here, or that's the right side of this figure over here. That's just like, okay, gas are uniformly distributed. You can calculate, or you can measure the pressure, you can measure the temperature, and everything just nice and cool. But during this process, right, well, you cannot represent this whole thing as a line, as a curve, or anything on PV diagram because it's ill-defined values. Cool? Does that help? All right. But then it doesn't help in terms of like, Ajahn, and how are we going to calculate entropy change then? Because, well, there's no PV diagram. All right. And here comes the key of this change in entropy, guys. It's path independence. Yes.
Okay.
So that means I don't care. I don't care if gas going from point 1 to point 2 or point I to point F in whatever way or whatever processes or whatever, I don't care. I can connect these 2 points using any curve. Does that make sense?
Okay.
Any curve. And then all you need to do is just calculate that Q over T, heat exchange over temperature, on the curve that you pick. You will arrive at the same value of delta S. So that means what I'm saying is you can just, okay, Ajahn, I'm just going to shoot straight like this. I'm going to use this line to calculate delta S. Fine, go ahead. Some of you may just say, Ajahn, I want to do this constant pressure first, followed by constant volume. Fine, use this line, calculate delta S. Some of you just like, okay, I just want to go constant volume first and then this. Fine, you do the delta S. Some of you just like going to go crazy. I want to explain this. I mean, I want to try this using elliptical curve or something like that. Fine, use that, go crazy. You're going to get all the same of delta S. Cool?
Okay.
That's what it means by path independence. You can pick any curve that you want as long as you just draw it on a PV diagram, calculate the heat from those curves. It's going to give you the reversible heat anyway because it's already in a PV diagram. Everything should be good. And take that calculation, compare them. You're going to get exactly the same value of delta S because S is path independent. Entropy is path independent.
Okay.
However, we want to be smart. We want to pick a curve that make us, can calculate that change in entropy very easily. What do you think that curve should be? Any suggestion? Maybe whatever you think is correct. All right, I trust you guys. Every time that we talk about PV diagram, I told you to imagine that there's always some isothermal curve. That's isotherms of us. And because these 2 points are at the same temperature, they must be on the same isothermal line, right? They must be on the isotherm, same isotherm. So that suggests, why don't we connect these 2 points using isothermal process? That would be so cool, and that would be so easy to calculate because we have done this so many times. Yeah.
Okay.
All right. So, and as you can see, I think I used the wrong. Well, I use I, but this one use A. Oh my God, that's my bad. Oh, all right. Anyway, point A, point B, point 1, point 2, point I, point F. I think you guys got the point. Okay. So going from point A to point B, I'm gonna pick isothermal process because these 2 points are on the same isothermal curve or isotherm. Yes. All right, let's dive into it, shall we? So I'm going to pick this curve because I know how to calculate very well. First of all, along this curve, T is fixed, T is constant. So once again, delta U is 0. So from the first law of thermodynamics, exactly, change in heat, the heat exchange will be equal to the work done by the system. By definition of the work, it's PdV. We already did this. P can be written as nRT over V. So far, so good. But what we want is we want the change in the entropy. So let me squeeze in here, guys. So what I'm going to do is I'm going to write it like this. ds is dq over t. It's like this. Yeah, cool. Yeah, that is the change in the entropy. Okay, then you can see that now t cancel. Now, when we want to find the total change of the entropy, all we need to do is just do the integral of this. All right, no problem. I'm going to integrate this from A to B. Once I get that, that will be our change in entropy from A to B. Okay, so let's do that. Once T cancel, you already come down here. NR is constant. I can pull it out from the integral here. All right, I can integrate this one. It's going to be NR, integral of 1 over V dV. And that is going to be NR log V final over V initial. And that's what you get right here. But you saw from this one, you're going from initial volume of V. It expands to twice as big. So it's going to be 2V at the end. So this ratio will give you 2. So that's it, guys. This process eventually have entropy increases because the result is positive. So it's a positive change of the entropy equal to NR log 2, guys. That's done.
Okay.
All right. And if you want, I haven't tried this one myself, but you can pick other curves other than isothermal process, and you can try calculating the heat divided by temperature and integrate them. You will end up with NR log 2 no matter what. All right. If you have a chance to try. But anyway,บอกอาจารย์ okay, good. I got delta S equal to positive NR log 2. And so what? What? What do you want from this? So the idea is this. There must be some conclusion or something that you can draw from this. All right. And this is the second law of thermodynamics, guys. It says entropy, it's either remain constant or increases. But okay, this one is sort of like a shorthand, sort of like a shortened version of the big whole thing. Because when I say entropy remain constant or only increases, it's the entropy of the whole universe. But this universe doesn't mean like a real universe at this point. But what I'm saying over here is it must be the entropy of the system plus environment. Okay, and in thermodynamics term, when you have system and environment, that's equal to universe. Okay, it's just the universe that you are interested in. All right. And something that's make it easier, Ajan, who will want to do this all the time? Don't worry. An example that we do most of the time and make your universe quite manageable is the isolated system. When you have something isolated from the rest of the real universe, that isolated system is everything that you have. And that is your universe under consideration. Does that make sense?
Okay.
So, for example, come back here. See, when you're staring at this, you have insulating wall. So that means this system of yours, okay, when I say system, now let me highlight here this, the gas and everything inside this container has been cut out from the rest of the world or the universe because of the insulation. You do not allow heat to exchange to the rest of the world. So this can be considered your universe because this is an isolated system. So this sentence is trying to say the entropy of this kind of system will either remain constant or only increases. You will never ever have decrease in entropy of any universe. Any universe means it's either your universe that you have limited amount of stuff that you are considering or the actual universe that we are in. Seriously. All right. All right. Not talking about the multiverse of Doctor Strange or anything. Yeah. But anyway, that's the way that the second law of thermodynamics is being stated. Entropy of an isolated system remain constant or increases. That's one way. However, this is the complexity of the second law. There are so many approaches to this statement, or there are so many ways that you can explain the second law of thermodynamics. Another sentence that explaining the second law is this: there is no heat engine that has 100% efficiency. All right, this one is kind of like, okay, if I explain briefly, because we learned about this one from Carnot engine. And then we were talking about the Carnot engine back in the day. We were talking about these two processes, right? The one that you do the heat exchange when you have temperature change, and the other one you do the heat exchange during constant temperature. And what you say is, all right, guys, if you want to have a heat engine, you must have some heat lost that you cannot access to it, and you cannot use that heat to do something useful anymore. And because you want to run a heat engine, it has to operate between two temperatures. So when you want to go from one temperature to the other, there must be some heat that sort of like inaccessible to you anymore. Too bad. That is an sorry. That is an irreversible process. And every time you have an irreversible process, yeah, your efficiency will be pretty much get lower and lower, right? That's what we learned from Carnot engine. So that's why saying that means because you do not allow things to go in a reversible process in any heat engine. So that means there's no way that you're going to get an engine that run at 100% efficiency. That makes sense because now you understand the connection between 100% efficiency and the reversibility. Okay. All right. If it's not enough, let's move on to the next. It's impossible for any process on its own to transfer heat from cool to hot. Okay, so this one is okay, but that's kind of fine because if you allow heat to transfer from cool to hot, so it means it will be conflict to the first statement over here that entropy has to be either constant or increases. Because if you allow heat to transfer from cool to hot, that means there is a negative change in the entropy in your system, and that's not allowed. Okay. So in conclusion, guys, this is it. So the second law of thermodynamics in connections with the calculation of the entropy change, concluding that entropy of the universe doesn't matter it's a real universe or the universe of yours that you are considering must be only two ways. It's either here greater than zero for an irreversible process or equal to zero for a reversible process. You guys see what I'm highlighting right now? And of course, for any system, you only have two choices: reversible and irreversible. So that means for the entropy to change, you only have two choices. It's either increase, the change is greater than zero, or stay constant. So that you have no choice. The entropy of our universe, the real universe, is actually increasing all the time. And that's eventually going to lead us to the heat death of the universe, guys. That is the end of time. Believe it or not. That's the end of time. So at that point, there'll be nothing anymore in this universe. Nothing, 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 nothing. When I say nothing, it just means there's no heat exchange. You don't have any irregularity in the universe. Everything is so uniform that you cannot do anything anymore. Does that make sense? Come again. You guys getting older cannot change. You grow old is irreversible. So your entropy of your body increasing all the time. Food gets spoiled, things turns bad, your table gets clutters, disorders and everything, right? So you need to spend work to arrange everything in order and everything, right? But after a while, oh, just disorder again, right? So yeah, everything seems to go in that direction. Water that is hot turns cold. Things that get super cold turns to room temperature. They are all irreversible processes. But what is the point of the nature is trying to do? What it's trying to do is they are trying to get to the place where there's nothing is going to change anymore. Does that make sense?
Okay.
The reason that we eventually dying because we want to be uniform with the universe. Being a human right now is non-uniform. This is so weird. And we have to maintain our body by eating food. We go against the nature a little bit in the sense that we have to maintain our being by eating something, keep our life going, on and on. So there is some irregularity happens in our universe, but the trend of the change is going toward uniformity of the whole universe. And that is the heat death of your new universe. Everything's supposed to be peaceful and quiet. Everything is supposed to be uniform. And to get to that point, entropy is increasing all the time. The best thing that you can do is just staying constant. So it means any process that is reversible, at least entropy is still the same. But because we already concluded that all the processes in this universe are irreversible,
Okay.
so that means, yeah, our universe expanding, entropy is increasing. Eventually, we're going to get to the end of time. And that's the conclusion of today's lecture right here, guys.
Okay.
Isn't that cool? I don't know, call it cool or not, but I hope you learn something. And this exercise gives you enough quantitative analysis to the entropy calculations. And I post at problem or the homework set 4. I'll give you a couple more examples that allow you to practice calculating the entropy change in simple system, and try those on and see how can you how you can calculate the entropy change in some simple scenario, like the coffee cup cooling down, ice melts, on, and look at the entropy change. What you're going to see is if the entropy change is positive, that means the process that you are analyzing is an irreversible process. That's it.
Okay.
Like this one here. We calculated the entropy change in this system, and this system is our universe. There's nothing else. It turns out going from left to right has the change of the entropy of positive n or log 2. Because this process has an entropy change that is positive, we can conclude that this one is an irreversible process. That's it, guys.
Okay.
Make sense? All right. So that's what it is. Before we close everything down here, actually, there is one more thing that I just want to mention, and I think is very cool. Number 2 right here actually has the deeper meaning, for especially for those of you that are doing computer science or computer engineering, all this stuff. When you look at this one, our system here, if I draw this borderline right there, that split this in half. And let's say, just for simplicity, you can look at the upper half of this container. This one still has no gas, but on the right, you fill up with gas. And I write as 0 and 1, right? So that means you can actually, practically, you can use this system to split between 2 states of something. When I say 2 state of something, it means it contains some information here. You can think of this as a yes. You can think of this as, maybe it's opposite, right? You can think of 0 as a no. You can think of this as a yes. So this is like a digital, same thing. So number 2 right here is like, actually it's 2 to the 1. So this is a 1-bit system, 0, 1. So that means this is the way that you can quantify the amount of information that you can store in a single system here. So imagine that if you have like a multiple containers over here, then you can have a bunch of 0, 1, 0, 1, 0, 1. And then all the configuration that you can deal with this 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, on and on, will have more arrangements built into your system. More arrangements means this number will increase. When this number increases, it means the amount of information that you can store in this system is going to be greater. And this is the way that you can quantify the amount of data in your system as well.
Okay.
All right. So for those of you that going to eventually hit with the information science and all this stuff, you will have a chance to look at how you quantify the amount of information stored in a system using the definition using the entropy definition. It's the same, pretty much like it's the same kind of definition that you're going to use there. Okay, so entropy is kind of cool in the sense that it's actually it's deeper to me. It's another level of explaining the nature. It's explaining how nature is evolving and what is nature is trying to get to. And to me, my conclusion is nature is gearing toward uniformity. Everything's supposed to be flat. It's supposed to be calm and peaceful. That's my conclusion right there, guys. Okay, thank you. That is it for our thermodynamics module. And don't forget to try exercises in the homework, and I will post the homework as the assignments, all right, for the set number 3 and set number 4. But for those of you that are concerned about submitting the answer, and if the answer of your submission is kind of like incorrect, and like, don't worry about it. I only want you to try, all right, and submit. The submission is just only proof that you have already given it a shot. So you already got 1 point for each assignment. Okay. So correctness of your answer, it's inconsequent. Well, inconsequent in the sense that for the purpose of the score. Okay, guys. The question is, will there be the assignments set 3 and 4 is coming. So I'll put those pretty soon. All right. But I will set the deadline of those assignment 3 and 4 to be the exam date. So you have plenty of time. All right. Don't worry about it. And as you have seen from assignment 1 and 2, it's like, you can type in like a simple answer and then that's it, you're done. Okay. So the exam day should be concluded tomorrow, right? Yes. So I'll wait until tonight. I think there are maybe 10 more people that haven't answered. But anyway, so we're gonna draw the conclusion either tomorrow or maybe just a day or 2 here. All right. Maybe I'll post another poll for you to choose between Saturday and Sunday, because right now it's so close to each other. Right. It's just like, yeah, it's 27 versus 26 votes right there. All right. So we were just gonna wait until the end of the day, and then maybe I'll put another poll on for you to pick between Saturday and Sunday, and that's it. All right. We'll set the dates there, guys. Okay. It's a take-home exam, 12 hours, but the material itself should only take about 2 to 3 hours. So it's not going to be like a 12-hour material for you to do the exam. All right. So doesn't really need that 12 hours. Okay. All right, guys. So thank you for sticking around, guys. I think that is it for today's lecture. And I will see you guys on Saturday. I won't miss it this time. All right. Thank you. Take care. I'll see you this Saturday. Bye bye.